Hello.
So that participants can see you and try to relate with yourself. Keep it on.
Yes.
Yes.
So good afternoon, everyone. So let's just recap what we have seen, what we have understood in the yesterday session. So in the yesterday session, we have seen what is the 3D printing and what are the differences between 3D printing and the additive manufacturing. Um, and then we have seen that why 3D printing is an emerging technology. How does it provide the support? How it is a potential backbone to many of the other industries like automotive, aerospace, smart factories, medical devices, IoT, and how does it being considered under the umbrella of Industry 4.0 technology? Why industries are moving towards the additive technology? What are the key advantages of that? Then what are the popular additive manufacturing technologies that are into the market that most of the industries adapt for their work process? Then we have seen what are the market trends in the additive manufacturing for the additive manufacturing. What are the other kinds of the industries which are adapting to this technology? How often or how much of jobs creations are there into this market, and what are the changings, what are the upgradations has been done since the industrial revolution till today's smart manufacturing methods that allow 3D printing to be one of the technology for this industry. Then what are the materials for the FDM technology? What are the standard plastics, engineering plastics, and high performance plastics? What are its key characteristics, and where it can be used, in what applications it can be used, whether it's basic engineering materials or the high performance FDM materials. Then what are the materials associated with the polyjet technology, and what are the advantages of using this technology? And what are the machine characteristics of the Stratasys FDM machines, which makes it a cutting edge technology, which makes it an industrial leader for many of the industrial OEM suppliers, even for the research purposes, and how reliable is this machine when you are doing the printing operation? How does it secure your printing jobs? And how what are the mechanisms that secures your geometrical freedom and the dimensional stabilities? What is the workflow associated with the FDM technology? What is the workflow associated with the polyjet technology? And some of the key examples from all over the globe, from different industries where 3D printing can be used. So there is no limit where you can use the 3D printing technology for your research purposes or for new product developments. And why 3D? Why does it make a very valuable technology or a valuable manufacturing method for the prototyping purposes or for the end use parts? So if anybody has any question related to the previous session, you can please ask now. Okay, then let's continue with today's session. So in today's session, we will learn about what are the file formats that are the standard formats for the 3D printing technology, for any kind of the technology that you're going to use in additive manufacturing, and what are the errors associated with it, what are the other alternatives for that file formats, and also about the GrabCAD print, which is a slicing software for the Stratasys machines, and what are the key characteristics of it, and we'll see a demonstration also for that software. So let's start with what is an STL file. So there is a video, a short video of what is an STL file and how does it, how is it different from the CAD format files.
Triangle-based mesh of a 3D design. Each triangle consists of 3 vertices and 1 normal. The normal determines the orientation of the triangle and also determines which side of the triangle is inside and outside. Material is deposited on the opposite side of the normal. A CAD file differs from an STL file in several ways. A CAD file is defined by its parameters, whereas an STL file is defined by triangles made of vertices and normals. A CAD file is therefore more precise, while an STL file is more or less a close approximation of the original design. Since CAD files are focused on designing for traditional manufacturing, it does not include any information about the inside or outside of your part. An STL file does contain this crucial information. This is why STL files have become the standard file format for 3D printing.
Okay. So you have seen what is the difference between the CAD formats and the STL files. So STL stands for the stereolithography. So this is the standard format files which has been introduced like the other CAD formats like for the NX, Creo, SolidWorks, CATIA, AutoCAD, or any other kind of the CAD softwares which you practice with your current processes. So stereolithography is a format which has been introduced with the 3D printing technology, and this stands for the stereolithography, and also in other terms, it's known as the standard triangle language or standard tessellation language. So when it comes to 3D printing, a CAD format directly cannot be used. So in the earlier cases, when the additive manufacturing technologies were invented and introduced into the market, so this was the standard file format, and till now it has been a standard practice for the 3D printing industry. So that stores the information of the geometry in the XYZ format, okay, in the triangulation method, and it is a single format uh, that can be exported from any of the CAD programs that you use. So this STL file is a combination of the tessellations. So tessellation is a process of tiling a surface. Okay, so suppose you have created an object in the CAD software in a 3D format, and when you convert that CAD format into the STL format, so it converts the surface and all the parameters into a small tessellation formats. Okay, which is I mean, and during the conversion it produces no overlaps or gaps. Okay, because if there is any overlap or gaps between the tessellation, that means that you are missing some data, okay, in your CAD file or in your STL file. So this STL file, it consists of the triangles and it covers up the whole surface in the 2D shape. Okay, and and another thing is that it cannot represent any color or the texture. So when 3D printing was invented, it was meant to only create the geometries, okay, to check its form and fit application. But there was no color or the texture that it can store into its file format. So also there is a process, okay, in the software itself when you convert the files through the SolidWorks or any kind of the CAD software. So there is a process through which you can tessellate your files. That means you can create the mesh as smooth as possible or as per the geometry that you are going to use. So on the left side, okay, which is you can see that is a very smooth sphere surface you can see. So that consists a lot of the thousands or the millions of the tessellation mesh surface files over the surface, but that will also enhance its the file size. So the larger file size was one of the issues that that used to hang up the process of the software or into the machine itself, that it cannot, that it is, that it was unable to read those files, that much larger files. So what happened, that the engineers and the companies, they introduced the tessellation process, okay, where you can decimate the size of the mesh surface, okay, and you can reduce the size of the meshes so that the file size will become smaller. Okay, so it will be easy to handle through the computer system, through the software, and also with the machine when you convert it into G codes. So the smoother the surface, the larger will be the file size. Okay, but if you just want to check the form of a particular design of a particular product, so you can decimate the file size. Okay, you can decimate the triangles on the surface. Okay, so the right side is, you can see it is a very coarse surface finish, but the size will be very, very small. So it will be very easy to handle through the computer system, through the software that you are going to use, and also for the 3D printer machine, which reads the control codes through the G codes file. So, what is the process that you need to take care when you are converting your CAD file into the STL file? So, when you are done with your design, when you're done with the design of your prototype or your product, so you can go to the save as option. There you save as of the export option, and there you can see the STL format. So, STL has become a very standard format, and that is it is available in all of the CAD softwares nowadays. So when you are choosing the STL file, you can also go to the advanced options where you can decide with what kind of the output you want. Okay, if you want the output in the millimeters or in the meters or the inches, there you can change the units. You can change the codes, like you want it in the binary code or the ASCII code. And again, you can change the resolution. So resolution means if your design is very big, okay, if your design is very big or it is an assembly part, so there you can customize the resolution of the particular prototype of the particular design or a particular feature also, and you can save it after that. So you can see the difference between the different resolutions, that how the, if you change the number of tessellations, how the resolution will change and how will it affect the geometry of that particular product. So if you are just going to use it as smooth, I mean with the smoothest resolution, so you will get the output like the first one, okay, the smooth surface with a good surface finish, and also the geometry uh, will be the best as possible that you have designed. In the second condition, if you don't want, if you just want to check the form of it, you don't want to do any dimensional checks on that, you just want to see the form of it, how does it come out as the output, you can choose as the coarse surface finish. Okay, that will make the process faster also, because there will be very less number of tessellation surface on the mesh file. Then on the optimal, it conserves most of your geometry and the dimensional, like dimensional measurements, and it will give you the output accordingly. And in the fine surface finish, it will be a heavy file to be handled through the slicing software or through the 3D printer mechanism, but it will give you a close to surface finish. Okay, there you can see a less number of tessellation faces on the surface in your 3D printed output, and uh, it will make your process much more easier and much more faster. So with a coarse resolution, if you pick up this setting, then the file size will be smaller for the larger triangles. That will only represent your geometry. Okay, it will allow you to build up the geometry in a shorter time. Okay, because there will be less geometry to print. But again, you will not get a good surface finish. So there will be some roughness over the surface, which you can post process it as per the as per the methodology you want to take. Then in the fine resolution method, the file will be of the larger size. Okay, there will be more triangles over the surface, but you will get a very good a smooth surface finish. Okay, and also the build time will increase. So even if you practice at your own, that if you make an object or try to build a sphere in the CAD software and you change its resolution, and uh, if you load it into the slicing software and check its build time, so there you will see the difference in the building time also. If the coarse resolution is taking say 10 minutes, so fine resolution output can take a 15 minutes or a 20 minutes of time. Okay, so that depends upon the how big the geometry is and how complex the geometry is. So in favor to save the time, when it comes to savor the time, okay, so many of the industries, many of the OEM leaders, many of the engineers and the researchers, when they do not want to do the functional testing, or if they do not want to use it as an end use part, okay, so they go for the coarse resolution because they want to save that building time, and uh, also it makes it much more easier to handle the smaller file size geometries. But when you want the end use part, okay, so suppose if you're going to make a part for the UAV or the for the drones or for the robots, so you can choose the fine resolution, because if you're going to use for the end use part, okay, so the resolution should be very fine so that it can conserve all your geometrical data. Okay, all the geometrical data will so that you can get the good dimensional accuracies and a very smooth surface finish, so that uh, you can fit the parts together within the tolerances that you have given. So what are the types of the STL file errors when you are converting through the CAD software to the STL file?
Tutorial, we will discuss various types of STL errors. An STL file is a file format that can be read correctly by a 3D printer. During the additive manufacturing process, an STL file of the original design needs to be created. Why is a CAD file not sufficient? Because a CAD file does not contain any information about the inside or the outside of the part, unlike an STL file. First, we explain why STL errors occur. Afterwards, a definition of the most common errors will be given. This should lead to a better understanding of each error that is given. This image shows where Materialize Magics is positioned within your additive manufacturing workflow. Magics is the link between your original CAD file and the 3D printed part. The first step, going from CAD to STL file format, is a conversion from parametric design into triangle-based design. This can cause multiple errors. Most of the CAD programs are not developed with the focus on additive manufacturing applications. Aside from conversion issues, design imperfections of the original design also lead to STL file errors. For example, a bad junction of several surfaces, or the result of a 3D scan. These bad conversions and imperfections make it impossible to print your design correctly. The STL file errors need to be solved first, so a fixing is necessary. Due to its long-standing experience in additive manufacturing, the Materialize Magic software is fully equipped to deal efficiently with many of the STL errors, so that the result is one entity of triangles without any errors and is ready for 3D printing. Now that we know why STL errors occur, and before showing how to resolve them, we can take a deeper look at the most common errors and provide a definition for each of them. There are 5 big main categories. The first type of error is inverted normals. Second, and often related to the inverted normals, we have the bad edges. Alternatively, we can have problems with the shells, with overlapping triangles, and with intersecting triangles. Let's go a bit deeper into each of them. So, before we start to print our file, we aim to have an STL without any errors. Therefore, we have to fix
Is the audio
inverted
does everyone can hear the audio?
Okay, sir, it is audible.
Okay.
normals. These form the first common STL error. In this case, an inverted normal points inwards instead of outwards, and the material is defined to be deposited on the wrong side of the design. A triangle with an inverted normal is called a flipped triangle. A flipped triangle can easily be noticed, since the backside of the triangle will be colored red. These flipped triangles will cause bad edges. In a correct STL file, adjacent triangles should always have two vertices in common with their neighboring triangles. If an edge is not well connected or missing neighboring triangles, it is called a bad edge. Bad edges will be visible as yellow lines on your design. The error bad edges can still be classified as near bad edges and bad contours. Near bad edges lay very close to each other, but are not properly connected, and can easily be solved by stitching. Several bad edges linked together in a closed loop form a bad contour. Bad contours can form a hole, but this is not always the case. A hole appears when triangles on a shell are missing. In this case, 3 triangles are missing. Through a hole, you can see the backside of other triangles. It will therefore look red in your design. A third type of error is linked to the shells. A shell is a cloud of uninterrupted triangles. Normally, one part consists of one shell. However, it is possible that your design has several shells. This can be due to noise shells and intersecting shells. Noise shells have an extremely low number of triangles, or have very small volumes. Noise shells often need to be removed, as they can cause problems during the slicing or printing process of your 3D printer. Besides noise shells, intersecting shells form another error. These are shells that partially occupy the same volume. If we don't clean up the intersecting shells, the intersecting volume will be printed twice while printing. This will cause overcuring or overheating of the material. For a successful print, this needs to be fixed. The fourth error is overlapping triangle. Triangles are overlapping if the distance or angle between them is smaller than a given tolerance value. These triangles can often be recognized as a zigzag form in the surface, likely to be less crucial for printability, but we recommend to remove them anyway, since these fixes will improve the surface quality. A last error, which we will discuss, is intersecting triangles. You usually will have these triangles if you have intersecting shells. Triangles that intersect need to be unified. We end with a summary of all errors. First, we have inverted normals. Then, bad edges, which consist of near bad edges and bad contours. Bad contours can sometimes be called holes as well. Furthermore, we talked about problems with shells, and more specifically, noise shells and intersecting shells. Overlapping triangles and intersecting triangles are the last 2 errors we discussed in this tutorial. To finalize, we will go in the software and review the most common STL errors with their corresponding color codes. The first one is inverted normals, which is indicated as a red surface. That is why the inside of an STL part is always red. Secondly, bad edges, including near bad edges and bad contours, are indicated with yellow lines. Let's go to another part to have a clearer image. This part displays a hole. Holes are indicated with an uninterrupted yellow contour, and you will also see the red on the inside of the part. The other circle has inverted normals. which means you can't see the inside of the part.
Yeah. So the errors that we have seen, the main errors which comes with the STL files are the holes or the gaps in the meshes when you're converting through CAD to STL, then the non-manifold edges or the non-manifold vertices, the overlapping or the intersecting triangles. So when two tessellation triangles, they intersect to each other, so they give you a very pointed or very bad surface finish, and also it hinders your geometrical form and dimensions also. Then there are flipped normals, which leads to the missing material extrusion when it is converted to the G codes. So what are the issues with these errors? Why do we need to take care that why this error matters when you are converting into the STL data? So holes or gaps in the mesh, they are, they are created, and they are the missing triangles in your on your surface geometry. Okay, when it does not share, when the two common vertices does not share, uh, does not match up, and it leaves a gap on the mesh file, on the mesh surface. So this kind of the error, it does not give you a very watertight uh, closed surface geometry, okay, which leads to the gaps and which leads to the missing data when you are converting into the G codes. Then there are flipped normals. So every triangle is calculated with a normal vector where it is facing towards 2. So in the normal condition, in the right condition, all the flipped normals should be facing outward of the geometry. Okay, that makes it an identity to be a perfect geometry in the STL model. Okay, if it is not in the outward and it is in the inward side, okay, then it needs to be flipped, okay, by using the third party softwares, and so that your geometry will be in a very good condition. Because if your geometry is very complex, okay, and if the errors are there, so it will not give you the output, that will lead to wastage of your time, your cost, and also it will leads to a very hectic operation when you're using that technology. The intersecting and the overlapping triangles, so these triangles, it does not give you again a good surface finish. Okay, if it is not corrected, it will inevitably leads up more time. Okay, it will add up the time and the cost to the process, that will make more material. Okay, so to avoid a failed print, you need to remove these overlapping triangles. Okay, you need to unify those triangles in the same plane, okay, with the repairing softwares, with the third party repairing softwares. Then there are the bad edges. So bad edges means that if the two triangles of the surface mesh, okay, if one point of the triangle is matching and the another is not, or there is a gap between the two triangles again, okay, if the edges are not intersecting to each other, that will lead to create the holes and the bad contours on the surface. So these bad edges, it results to the it shows the error in the software itself. When you are slicing the geometry, it will show that it will not be a printable file. Okay, so you have to patch, and you need to blend those bad edges together in the repairing softwares. Okay, and that will give you a very high quality object, and your printout, your 3D print output will be in a very good surface finish, and you will not use your tolerances also in that manner. So what are the advantages and disadvantages of STL file? So since this STL file has been introduced as a standard format, and globally in all the technologies, it is still being used as a standard format. Okay. So there are certain advantages, but also due to the errors, there are certain disadvantages also. Okay, so the advantage is that if you want a product in a single color, or in a single type of the material, then STL is the best file. Okay, because STL file uh, will consist of less data. It will only consist your only geometrical data. It will not consist your any color information or the material information into the file. So it will be very easy, simpler, and smaller in size, so that it can be processed faster than the larger file other formats. The disadvantage is, so when you want to use for the multiple color or for the multi-material capability, or the multi-material parts like the over-molded parts, or you if you want to mix two materials together, like yesterday we have seen in the polyjet technology, you can mix two materials together. Okay, you can form up new color combinations or the new material combinations by mixing up of more than two materials at once. So seven materials at once can be mixed together to give you a color information or new material information. Okay, so in that manner, STL file is not the right choice because it cannot store that data. So and also STL files, they encode only the surface geometry and not the color or the texture. And the another issue is that during the when it is, since it consists of the tessellation files. Okay, so all the uh, so if your profile has a curvature, okay, so the STL file, the mesh files, it creates a kind of the step case effect. So like if you see the steps, okay, if you see the staircase, okay, so stair steps are the have the edges at the end, have the sharp edges. So that kind of the surface finish you will find on the 3D printed object if there is a curvature and if it is not in a very fine resolution. If it is in a coarse resolution, so you will find very bad edges over the surface that will not give you a good surface finish or good output, and it can also hinder your geometry form also. So these are some of the advantages and disadvantages for using the STL file. So let's see what are the alternatives related to the 3D printing industry. Okay, what are the new formats has been developed looking at the disadvantages of the STL file formats. So the first is the OBJ file format, which is the object wavefront format. Okay, this format has used with relation to the scanning and with relation to store the color and the texture profiles. So many of the softwares like the Max, Maya, Blender, where you can work upon the organic modeling or very fine curvatures, and you want to apply some textures or the color information over the surface, over the object. So in that condition, OBJ file formats has been introduced, and now the 3D printers can support those formats. Then there is a PLY polygon file format. Okay, so this is also being developed for the 3D scanning objects. So in the case of using a 3D scanner, you can get the output in the OBJ file, PLY file, and in the STL file format also, depending upon what kind of the data you require for the further processes. So in the PLY format, since it's a polygon file format, it can store the color, it can store the transparency. Okay, so if you scan an object which has some transparency, which has a color information over the surface, uh, so that can be captured with the polygon file format, and it will also capture the texture coordinates. So if there is any texture like the leather texture, wood texture, or stone texture is there, so any kind of the textures can be scanned, okay, and can be stored in the polygon file format. And also the data values like your XYZ values, geometrical values in the three coordinates. Then we have a new, this is a very latest file format introduced into the 3D printing industry. So this 3MF file, 3D manufacturing file format, it is, yeah, it has been published by the 3MF consortium. So it is an organization, it is a society of additive manufacturing. and this format has been introduced with the association of the statistics, so that it can support many other technologies and many other softwares also into the market. So this file format, it can store the information of materials. Okay, so what material that you're going to print. So suppose if you're going to print an ABS material, polycarbonate, nylon 12, ultim material, so you can store that information while designing the CAD file into this format. The color informations and all the other informations that cannot be represented with the STL file format. Then there is a additive manufacturing file format. So this is again a new format introduced. So this file format, it is being used to specify the material and the color of each volume. Okay, so each volume means that at every surface or at every triangulation, okay, if there is a change in the material or in change in the color, okay, so with that much of the accuracy, with that much of the details, you can store into this format and you can use it for the supported 3D printing technologies, where you can print the where it can intake the information of the material, color for each volume or color for each triangle in the mesh. So you can see in the photo, okay, so this is the mesh file and this is the geometrical file. So you can see how the color variations are there from top to bottom. Okay, so this file format can store the color information at each triangle in the mesh. So these were the file formats and these were the errors that has been used or that is being used globally with all the 3D printing technology, and that is being used as the standard file formats. Now we are going to see what is the GrabCAD print software. So GrabCAD print software. So with every 3D printer, so whether you use any industry 3D printer, okay, every machine has a software to process the file. So these softwares are known as the slicing softwares. Okay, so GrabCAD print is a slicing software that is being developed through the Stratasys and for the Stratasys machines only. And it brings upon many advantages and many advanced features that is being very much used, and through the feedback of our existing customer, we develop new features into the software. We introduce new features into the software as per the feedbacks we get from the customer from all the industries like the aerospace, agriculture, automotive, farmer equipment manufacturers, or from the healthcare industry, consumer industry, or for the smart factories users. So all these users, all the customers, they give us the feedback, and we try to develop and we try to input those features into the software. So the software has been developed a lot, and there are so many good features that you won't find in the other competitive softwares for the other 3D printing technologies. So this is a short video how GrabCAD print software is usable for the 3D printing industry, and how much easier the process it can make for the user without any interruptions, without any going into the deep knowledge of what print speed you want to give or how much the temperature you want to maintain, what materials that you are going to print, and what is the ambient temperature you want to maintain in the machine. So all these features, it makes it much more easier through the help of the software and also the hardware in the machine.
Digital manufacturing. While unquestionably the future, it's no secret that we're not quite there yet. The biggest problem? We're not as connected as we should be. With GrabCAD from Stratasys, we're building a platform that brings connectivity and accessibility to digital 3D printing ecosystems. First, we brought you the GrabCAD community, a free collaborative space where over 3 million engineers hash out ideas, find inspiration, share knowledge and CAD files. Then we took it a step further and built GrabCAD Workbench. And now, GrabCAD Print is taking the mystery out of 3D printing. Take a look. Want to have your CAD and print it too? Now you can. No more wasting time converting to STL. No more dumbing things down. Just view and print your CAD in all its high-res glory. Get visibility into available resources, see printer schedules, check printer status, queues, usage, and errors all from one window. Control multiple printers and technologies from a single app. Remote teams rejoice. Connect to the cloud to schedule a print and receive notification on its status. With mobile monitoring, you can check on your progress from your desk, home, or anywhere in between. 3D printing has gone without serious business intelligence for too long. So, we fixed that. Reporting and analytics features allow users to see business-critical data in real time by material, printer, project, and team. Community, Workbench, Print. This is just the beginning. Together with some exciting partners, we can shape the future of digital manufacturing. Learn more at grabcad.com.
Yeah. So the workflow, which was being followed through the conventional processes, through the other machines in the when the 3D printing was introduced. So the initial method was the conventional method was that the engineer used to design the files into the CAD software, and those CAD softwares used to be transferred to the printer operator, and the printer operator has to prepare the file into the third party softwares like the Insight, Magix, Netfab, Object Studio, Solid View, Catalyst. So now the Stratasys uses the softwares. Now the Stratasys has the softwares like the Insight, Object Studio, and the Catalyst. So these are the Stratasys software which were being used in the older models or the older generation of the 3D printers, and which provides the particular features and the particular functionality to the FDM technology and the PolyJet technology. So now with the introduction of the GrabCAD print, it has they have streamlined the design to print workflow. So there is now only a single software which you can use, okay, for all the 3D printers on the for the Stratasys platform. So whether you're going to use a FDM machine, FDM technology, or a PolyJet technology, you don't have to switch to the third-party software or any other software. Okay, you can use a single software for the FDM technology and the PolyJet technology, and the work process has become a very simple. So the designer has to make the design in the software, and they can directly export that file. Okay, you don't have to even convert that into the STL file format now. So GrabCAD print supports all the native CAD formats now, whether it is from the SolidWorks, NX, Creo, CATIA, whether it's an assembly file or an individual file, part file, and the standard files, shareable files like the IGS, STEP, STL, OBJ, PLY. So there are many file formats that is being supported now through the GrabCAD software, and that has made the work process much more simpler. And there are also more interesting features into the software which we'll talk about. So more about the professionals, users who uses a 3D printing technology from Stratasys. They can be connected through the 3D printing operation through the desktop application, cloud connected, and you can also access the ongoing operations, the ongoing 3D printing operations through the mobile apps. Okay, so if there is a operation, there's a 3D printing operation going in the premises, and you are not available in the premises, you are at your home, or you are at some another location, okay, outside the city, okay, and if you want to see that how the print is going on, how the job is working on, if it is a very big job and you want to monitor it. So there is already a pre-installed camera inside the machine. Okay. And through the cloud connected desktop application or through the mobile app, you can access through your username and password, you can connect to your machine through the network connectivity, and you can access the all the print jobs that is being in the queue, and you can also monitor through the mobile cam or through the camera app or through the camera that is being installed inside the machine. So it has made much more convenient, and it has provided the solution, you know, a single step solution. Okay, a single stop solution, so that you don't have to rely upon, or you don't have to purchase a third party softwares for these kind of the functionality. So the GrabCAD print, it comes up with the 3D print of preparation. Okay, so you can do the normal 3D print preparation where you can do the orientations, optimization, and select the support generations. You can print any kind of the format files like the STL, VRML, native CAD file formats like from the Creo, SolidWorks, CATIA, NX, Inventor, OBJ, and you can also repair the damaged files. So if you're using a third party, if you're converting into the STL file formats, and if it consists of any of the errors that we discussed, so this software itself, it will detect those errors and it will repair those damages into the software. Okay, for which earlier you had to purchase a third party softwares like the Magics or the Mimics, you have to purchase it, or the NetFab, and those are the licensed softwares uh, for which you have to pay annually. Okay, for the commercial purposes you have to pay it annually, and but all these features, all those important features where you can repair those damages, repair those errors on into the files, so that is being integrated into the GrabCAD print software now. You can get the real-time notification. So if you're not into the office, you have given a print job, it's an overnight job, so it will give you a notification when uh, if there is any error or when the print is finished. So it will keep you up to date how is the machine working at the premises, and if you're not there at the location. You can also monitor your print jobs, and also you can see through the camera installed in the machine. There are advanced FDM control functions which we will discuss later. You can also monitor, and you can access the multi-printer inside the premises. So if you have the multiple printers with the FDM and the Polyjet technology, so you can use a single software, okay, a single application through which you can control all the printers with a single system. You can even schedule your print jobs. So if you get the print jobs, like tens of print jobs in a day, and you have to schedule it as per the urgency, as per the necessity of that print job, so you can schedule it accordingly. The printer operator can schedule the jobs accordingly on the basis of the needs. uh, and also there is a security. So GrabCAD print is it's rely upon the best in class network architecture, so that it cannot be accessed through any kind of the third person except you. If and you can access these softwares through the mobile app and the cloud based desktop application through the username and the password. So these are the important features that the GrabCAD print brings along. So you can see in the photo itself that you can import the STL, SolidWorks, CATIA, Wavefront, Solid Edge, Creo, Parasolid, VRML. So any kind of the user, any software user, okay, can easily use this machine, can easily use this software, GrabCAD print software. You don't have to purchase a third-party software, or you don't have to convert it into the STL file formats where it can lead to some errors. So you can directly import now the CAD native CAD file formats. Also, you can see the job history. So how much time was there? You can calculate your weekly use, monthly use, or the yearly use. That how much the material has been consumed yearly, how much the time the printer has run, how many hours of the printing jobs you have done over a period of time. So there is one more latest feature that has been introduced into the GrabCAD print software. So this is a short video related to it.
My name's Eric Fickus. I'm a senior industrial designer. I do a lot of 2D, but I think my interest and my expertise is probably 3D CAD, rendering, animation. So what we have is a concept that we developed in 2D. It's a two-part clamshell Bluetooth speaker. These two halves will slide together. Then you pull them apart and it reveals a speaker on one side and controls on the other. We built the model in SolidWorks and then brought it into KeyShot and then added all the textures. Being able to do the speaker grill as a displacement map was really fast, and we could change the grill on the fly. And it's minutes to do versus hours or days. And we've got a bunch of different concepts that we did. So we have a couple of material textures, and we've got a couple of wood textures. Once we have all the textures and the bump maps and the displacement maps in place, we can save the file out in a format called 3MF, which is new to KeyShot. And this 3MF file format keeps all the wood grain and all the image maps, displacement maps, bump maps. It keeps all of that, and it saves it in a way that's now printable from KeyShot, which is just amazing. And we brought them into GrabCAD Print. I've imported 5 different models with 5 different wood textures. It checks the models. If there's any problems, we can run a repair on it. And then we can hit print, and it will build these parts on the J55. We were able to run this on the J55 machine overnight, and we have real physical parts in a matter of a few hours and have something that was completely convincing. Being able to do that overnight is something just sort of brand new. We had 5 different wood samples, and then we had different fabric samples, and we've never been able to do that before. You know, to rapid prototype a wood texture would have been just a heck of a lot of work, you know, finding vinyl or paint or faux finish or something like that on a physical part versus being able to print this overnight is just a real game changer for us. Just being able to assign these materials in KeyShot and then run the parts overnight was amazing. It's that new and special and different. It's really incredible.
So in this video, you have seen that now even for the aesthetic purposes, if you want to develop your parts for some aesthetics, if you want to apply some aesthetics over your part through the KeyShot software. So now KeyShot software is equipped with the 3MF file format, which can be used as a direct file format for the GrabCAD print software. So now we'll jump upon the a demonstration, a tutorial on the GrabCAD print software. So if anyone has doubts, you can please ask.
Dear participants, if you have any doubts, any questions, or any queries, you can ask.
Or is it possible to make the complex structures?
Yes. So it is possible to make any kind of the complex structure. So suppose if you want to make any farming equipment, okay. So suppose if you want to make a seed feeder, okay. So any kind of the sharp object which has some very complex profile, very complex contours over the surface. So you can make those complex structure with the 3D printing technology. So that is the difference between that you can see with the subtractive and additive. That with subtractive, you have to cut out the material to achieve that level of surface finish, to achieve that level of the accuracy for the dimensional stability. Okay, and that can use many of the advanced manufacturing process as per the complexity of the geometry. But in the case of the 3D printing, since it's a process of the manufacturing the part layer by layer, so there is no wastage of material, and also the material is extruded, the material is joined only on those areas, okay, where you require the material. Where you don't require the material, it will not extrude the material in that area. So in according to that, any kind of the complex geometry, or however the bigger the size is or smaller the size is, however the if you have some small wall thicknesses, okay, which can be made only through the injection molding in terms of the conventional processes. Now that also possible with the 3D printing process.
CAD or STL, which one is best, sir?
So in the conventional processes, STL is still a very widely used format. Okay, so wherever you practice for 3D printing, you will see STL as a standard file format. So it depends upon what machine you are using, what software you are using. If it is able to intake uh, any CAD format which you are using, so if you are using SolidWorks, if you're using AutoCAD or CATIA, Creo, if the slicing software has the capability, has the feature to import the file, okay, then that is the best solution. If it is not there, then STL is the standard format. But you need to make sure that there are no errors into that STL file when you're converting it through the CAD software. Because if there are any errors on that, uh, in that condition, it will lead to some errors or some defects on your 3D printed output uh, during the process. Yeah. So STL is will not be the best, but if you don't have any option, then make sure that it does not consist of any damages or any kind of the error issues.
Yes, again, anyone? We will proceed for further. Okay, sir. I think no one has any. We can proceed.
Hello, sir.
Yes.
Yes.
Hello.
Yes.
Uh, for for creating good STL file, what precautions should be we taken?
Okay, so if you're using in the CAD software, whatever CAD software you're using, if there is any advanced option where you
Okay.
can change the parameters for the STL file, so you can change the code's resolution, you can choose the which code you want to use. So if it is a very simple geometry, if it is not very complex, you can choose the binary code format,
Yes.
okay, to be stored. But if it is a very complex object, okay, if there are so many features like holes, bosses, or grids are there, or the very small thicknesses are wall thickness features are there, so you can store it in the ASCII codes.
Yes.
And
Okay. Thank you, sir.
and yes, also in many of the softwares, if there are errors into the STL file, so many of the softwares are capable to show you the errors, but only in the GrabCAD print software it is capable to remove those errors, to remove those damages, to repair the files. So GrabCAD print has an integrated option, but for the other slicing softwares, you need to purchase or you need to use a third party repairing softwares like the NetFab or the Magix.
Okay, sir. Thank you.
Okay, so this is the GrabCAD print software. This is how the user interface looks. So here is the build volume. Okay, so first of all, you can choose what machine that you are using or which machine you are going to use for your 3D print operation. Okay, so in this list, it consists of all the Stratasys models, all the Stratasys 3D printer models for the FDM machine and the PolyJet machine. So it has all the older models and also the latest models which has been introduced now. So you can choose what particular model you are going to use. And if you have an in-house Stratasys 3D printer, then you can directly connect it through the IP address or through the network cable, and it will detect which machine or which model you are using. So it will show you which machine you are currently connected to. So here I have selected a Stratasys F170 machine. So this one has the build volume of 250 by 250 by 250 mm. So that is a 10-inch cube. So if you go to the file option, you can load up new projects. So you can save the projects into the GrabCAD print formats, and you can share those projects. You can prepare your file, okay, all the settings, and you can send those project files directly to the printer operator, okay, so that they don't have to choose any features or you don't have to explain about the geometry. You can prepare a file on your own and you can send to the operator or to the user of the machine so that they can directly open up the file and give it to the print. And in the models, if you add the models and if you see the file formats here, okay, so it consists of all the major native CAD file formats and also the shareable STL, IGS or the step file formats also. And you can also import the STLs as assembly. Okay, so suppose if you have make an assembly product, okay, and you want to 3D print it, so you can 3D print it with the FDM machine, Stratasys FDM machine, because it uses the dissolvable soluble support. You don't have to make the parts individually and then assemble them together. You can also print the full assembly as it is, okay, without dismantling the part and then assemble the part together after 3D printing. So you can import the file as assembly, the Stl files, which makes a much more easier function for the user. So here I will load a model here. Okay, so suppose if you're going to make a uh, mounting body, okay, for the drones or for the robots or for the AGVs, okay, where you want to maintain a connecting rod or the wheels or any kind of the frames that you are going to make, if you want to make for your particular product. Okay, so this kind of the design optimizations you can do so that it can save up your material requirement, okay, your material consumption, the cost of making of that part, and also the time of making of that part. Okay, so when you calculate, so in the manufacturing, if you're going to manufacture something, you have to consider all the calculations, okay, because you have to consider the cost of making of that part also. So if you you can you can decrease the cost of making by optimizing those designs. Okay, so you can cut down the material in your designs wherever where you require, you can optimize those designs accordingly. Where the loads are not there, where the stresses are not much there, where the vibration stresses or the loads can be can be taken care of. So these kind of the optimizations can be done prior or before 3D printing. And and the work process, so let's see how the work process goes on. So first of all, you can change the units. Okay, so suppose you have made the CAD file in millimeters, okay, but you want to print it in inches. So you can simply select it into the inches. So what it will do, if it is a 2 mm in the original dimension, it will convert it into the 2 inches. Okay, so it will simply convert the units, not the number, but it will convert the unit in that manner. Now for the tray settings, in the tray settings, you can select which material you want to print this part in. So you can choose, so in the F170, it supports 5 materials. So you can print it in PLA, ASA, ABS, TPU, ABS carbon fiber 10. So this is a newly introduced material. It's a composite material of ABS and carbon fiber. So it consists of the 10% chopped carbon fiber weight to weight with ABS, and it provides a very good stiffness to the part. So an application where you want a lighter weight but with very strong, with very high stiffness ratio, you can choose the ABS carbon fiber material in that condition. Then after the choosing of the material, so suppose if I choose ABS, now I can choose the slice height. Okay, so slice height is, so additive manufacturing, 3D printing is a process of addition of layers. Okay, so at a time it will deposit the material in a layer, okay, in a 2D layer, and addition of those 2D layers, it gives the output as the 3D geometry. So the layers, the thickness of those layers can be decided here. So it depends upon the how big the size of geometry is, or how complex the geometry is, how good surface finish you want, okay, in the output object. So you can choose the surface, or you can choose the slice layer, slice height accordingly here. Then the support material is by default a QSR support, which is a dissolvable support material, and it will also show you the support tip. So it uses a single tip. You don't have to change the nozzles here. So what happens in the other FDM 3D printers, if you want to print a very minimum layer thickness of say 100 microns or 150 microns, you need to use a particular size of the nozzle. And if you want to go for like 0.250 microns or 300 microns of the layer height, then you have to change the nozzle in that printer. Okay, but in this machine, Stratasys has the patented extruder and the patented nozzles, okay, which can toggle up, which can control the thickness of the layers within a single nozzle. Then the part build style, you can choose it. Okay, so normal means that whatever the infill density you have chosen to print this part, it will continue in that format only. And if you're going to choose in draft, so what it will do, it will reduce the infill style, it will reduce the infill density. So suppose if you're if it is only 100% by default, so it will reduce it to 50% or 40% of the infill density as per the solid portions or the geometry of the model. So I'll show you what is the difference you can see. So if I estimate the time, okay, with the normal part build style, Okay, so in the normal build style, it is taking about 53 minutes. And if I choose the draft, so the time difference you will see here, not much. Okay, it will not show you 53 in against of 40 minutes, but because geometry is very small right now. Okay, sorry. Okay, so in the draft mode, it will consume only 36 minutes. So it totally depends upon what end application you have. Okay, how much faster prototype you want, how much the necessity of that prototype you have, so that you can choose it accordingly if you want a normal build style or a draft build style. Then after selecting your material, slice height, and the build style, you can go to the model settings. So in the model settings, okay, so in this you can choose the object, and here you can choose the infill density. Okay, so there are various infill density, there are default infill density, and you can give a custom build density also. So minimum, because of the size of this part, it can take a minimum of 45%. But if I scale it up, so suppose if I scale it at 150%, okay, again the size is not much. Okay, so the minimum here, yeah, sorry. If you choose the sparse, so you can give it the infill of minimum of 23%, because this much, so it calculates the software, it calculates how much of the minimum infill density will be, will be good for that particular geometry to make that part and to maintain the minimum strength into that part. So you can choose the different infill styles. You can choose a sparse, sparse double dense. Okay, so it's a zigzag combination. Okay, this one also you can choose. This is hexagram. So with the variation of the infill density, you will get the variations in the internal strength also. So that will give you a freedom here. The software gives you a freedom here. How much of the internal strength you want to maintain into that part. If you want 100% fill density, you can just directly select a solid settings. And these features I will explain to you when we will discuss about the advanced FDM. Then we can select the support settings. So there are various support settings also, as you can see the settings of the model infill density. So in the smart condition, you can see up here in the smart condition, the supports will have the sides, reduced sides, okay, in the tapered form, and it will consume a very less supporting material. In that condition, the sparse will have the same pattern as the model sparse settings. The basics, that means that it will create a denser pattern, okay, without any contour of the model related to the model. The surround support settings, what it will do, it will create a surrounding support structure for that geometry. Okay, so I'll show you some example of this. So suppose if I select smart and I select sparse double density, okay, at 57%. Okay, so it will show you the estimations also in real time, that how much time it will take to print, how much model material it will use, how much of the support material it will use. Okay, I got a question that how much time it takes to print the object on the screen. So here you can see, you can estimate the time. Okay, so whatever the time it is showing, okay, you can add 10 minutes to it, because it takes 5 to 10 minutes to for the machine to prepare it, to prepare the ambient temperature, to heat up the nozzles, to load up the material also. If you have not loaded it, if the material is not already loaded, then from loading to machine preparation, you can add up 10 minutes to it. Then after that, you can just simply add up this print time. So this 5 hours of time it will take to print, and it is the very nearby print time it will show as per the model that you're using, or it changes with the material use also. So if this right now I am estimating at ABS material, so if I choose the ABS carbon fiber uh, or the TPU material, thermoplastic elastomer material, the time will change again. Okay, because for every material, how much time it will take to melt the material, okay, before starting of the print job, and switching between the model material and the support material. So time changes accordingly, the geometry, the parameters you have set, the orientations, and also the material that you are printing to. Also, you can see the slice preview. Okay, so before starting your print operation, okay, before you actually start your print operation, you can see that how the layers are going to deposit on the build volume. So the green color shows the model material, and the yellow color shows the support material. So here on from the top you can see, so I have chosen the support as the smart support, and infill I have chosen the spark dense at 57%. Okay, so you can see that layer by layer how it is depositing the material. Okay, so I have chosen 57%, so you can see the gaps between the layers. So how does it start? It starts with always creating the walls of that particular layer, of that particular section of that geometry. Okay, so this particular section is a circle, it's a ring. Okay, so in this ring, it will first of all deposit the material, the outer wall and the inner wall material, and then it will infill the material between these two walls. So this is how the 3D printing works. This is how the FDM technology works. So here you can see that how the supports are generated with the smart feature, and the model material with the 57% infill density. Okay, and you can also see that at the edges, okay, at the edges of that particular slice of that particular section, it has infilled more material than the rest of the volume, right, than rest of the area. Why? Because there is an option here which is the body thickness. Okay, so here you can maintain that what at a particular no matter if you are, even if you are going to infill it at 20% or 25%, 30%, 50%, 80%, okay, it doesn't matter. You can even choose with less infill density, you can choose the body thickness, that how much of the body thickness, how much of the wall thickness you want the material to be completely solid. Okay, so here the body thickness is at 1 mm, 1.06 mm. If I increase it, okay, at say if I give it a particular say 1.5, okay, and if I estimate slice the part again, okay, so you can notice that even the time has increased because I have changed the wall thickness. I have increased the wall thickness from 1.06 to 1.5 mm. So that means it will consume more material now. Okay, at the wall thickness at all the sections of the layers. Okay, if now you can see that at the from the outer wall thickness to the inner wall thickness of 1.5 mm, okay, it has filled most of the material now here. Okay, here you can see it. Okay, so now you can see that from the outside surface of that of a particular section, from the outer surface to inner surface, okay, it has calculated 1.5 mm of thickness, okay, which it will complete, which will on which the model will be deposited completely, okay, and after that it will infill the inside material with the setting which we have chosen at 57%. So this is how you can change the parameters as per the geometry or as per the application, as per the load going to bear on that particular part, on that particular product. So this is how this setting of infill density and the body thickness makes the variation into the infill, into the strength, internal strength of the geometry, and also to the printing time and the material consumption. Okay, so if I choose the sparse material here, and if I change the settings a little bit, okay, so that was the double dense sparse infill style. So that means it forms the infill into the zigzag form, which gives a particular internal strength. But if I choose now the hexagram, okay, if I choose the hexagram setting now at 1.5 mm body thickness, and if I choose a sparse support style, so let's see what are the changes we can see into the geometry. You can notice that in the graphics, okay, so on the screen you can see that there are sharp edges on the surface, okay, all over the geometry. Okay, this is because of the because of your computer graphics also. If your computer graphics does not support high-end quality graphics. Okay, so that will also change up the your graphical view of the geometry in the software. But that doesn't mean that it will give the same output, okay, with the sharp edges in the 3D printed object. It depends upon your computer system configurations also. Because this file size is, because this is a very small file, okay, it's a very small geometry, but it is a file size of around 12 MB. So it's in an STL file, it's a very large file to handle also. Okay, so if if there is a file of 1 MB, 2 MB, or less than 5 MB of the file, okay, and the geometry is big, okay, say if it is a big of 100 mm, 200 mm, or 300 mm of size, okay, but the file size is only about 5 MB or 10 MB of the file, that it means that that file has been tessellated a lot. It has been decimated with a very reduced surface finish, a very reduced number of tessellations over the surface, okay, which will lead to the can lead to the bad edges, which can also lead to the rough surface finish. But that can be used as a draft file also to just confirm the your geometrical form. So now let's see what difference we can see here. Okay, so now you can see that the pattern of the support structure has changed, right? And even the infill density structure also has changed. Okay, so earlier you could see in the sparse double dense that it was forming a zigzag formation of the infill density, okay, which provides a much more uh, internal strength, okay, into the geometry. The hexagram provides a much further, okay, it makes the part lighter also, because the wall thickness of every strand of the line, okay, is very small, but it makes a pattern in such a way that it will provide a very good impact internal strength. Okay, so if there is any impact on the outer surface, it will be able to divert those forces, okay, inside the geometry, and it will able to take that load or the forces on the object. Okay, if I choose a much more higher density, okay, if I choose it at the high density, and if I again change the support style, so suppose if so every support style has a particular meaning. So for the surround support structure, so if you have a structure which has a very small thickness, and if it has a very smaller area in xy coordinates, okay, so suppose if the base contact, okay, if the base contact of the particular geometry is very small, and the part is in the z direction, okay, if it is a vertical object, suppose there is a rod you are printing, or if there is a particular uh, a body part you are printing, okay, and its wall thickness is just at 2 mm or 3 mm wall thickness, and you are printing it in the z direction, and height is about 100 mm or 200 mm of the height, then you can print with the surround support option, which will provide a surrounding support to that particular object, so that while printing it will not deviate from its position and it sticks to the build plate. Because if the contact surface area is very less, okay, like 2 mm, 3 mm or 10 mm of the support area, contact support area is there. So contact support area means that how much of the area of the first layer or base layer is connected to the build tray. So that is the contact area to the build tray. So if the contact area is very less, okay, and the part is in the Z direction, okay, in that condition, you can choose the surround support material so that it can provide you the surrounding structures to support the height of that particular object. Now, even if you see the estimates here, so when we chose the first setting at the 23% infill and the smart support structures, it was taking about 5 hours. So when I'm changing the infill density and the support density, okay, without changing the dimensions of the object, without scaling it down or scaling it up, okay, it is changing its printing time, and it is consuming and it is also changing the consumption of the material. So since I'm using the surround support structure option, it is consuming much more support material than the previous. So here you can see even now the support structures here you can see. So with the surround option, it is providing a surrounding support material, okay, on the sides of the geometry. Okay, so this can be used in a condition where the contact surface is very less and the geometry is more in the Z direction in the vertical manner. So if you're printing a rod, if you're printing a sheet of the part, okay, body part, if you're printing, okay, of the drone, or if you're printing a wing of the drone, or the, okay, so in that particular condition, this is the best setting which you can use for the support structure. You can use the surrounding support structure so that it will give you it will give the part the surrounding support, and it cannot discontact from the build tray, okay, and the part goes without any interruption. So now here you can see that I have increased the infill density here without changing the wall thickness that I've chosen at 1.5, the surrounding support structure. So you can see even the pattern here. So in the slice preview, you can see that what at what particular setting, okay, and what will be the best setting is possible for that particular geometry. So suppose if I change this geometry now, okay, so suppose if you have a geometry like this, okay, a mounting rod or a mounting bracket, okay, where you can insert the rods or any kind of the movable or bearings at the center and the rods at the end of the part. Okay, so this kind of the part that you want to make for the robots or for the drones or for the AGVs, or any kind of the farming equipment or any kind of the mechanical mechanism that you want to make. So in that condition, you can optimize the designs like this, where you can decrease the material consumption. So there is an option for the auto orientation. So this calculates. So if so, suppose if you had make the part in the CAD, okay, and when you load the part, it gives you the default orientation in the diagonal form, okay, in the diagonal coordinates. Okay, it is in the air. It is not contact the surface area. There is no contact surface area. Okay, the only edges are connected to the build tray. Then you can choose the auto orientation option. Okay, and the software will calculate the best orientation possible, where it maintains the strength of the part, consumes less material, consumes less time to print it, and which makes it much more easier and much more faster to print it. Okay, so this is the best orientation that made it possible. So this is, if I keep it aside here, and okay, so you can see that this is showing the best orientation possible for this particular object. So there is also a reason why it has chosen this surface and not this surface. Okay, you can manually rotate it. Okay, you can even manually rotate the part also in any coordinate, but this surface is not a flat surface, as you can see here on the screen. So this is a very irregular surface, and this is not a flat surface. So in such condition, always remember this point, that the contact area should be a flat surface with the build tray, so that it gives a much more larger area to be connected while it is 3D printing the complete object. If the object is longer, if it is taking a much more time of 5 hours, 6 hours, of even the 50 hours of print time, okay, make sure that the contact surface of that particular object is always the flatter surface to the build tray. Okay, so here if I change the model settings again, if I change the model settings here, and if I change the wall thickness here, say at now if I give it at 1.8, okay, uh, and if I change the support density, okay, if I change it to the box, so what output it will give you. Okay, so let's see that how it will show the slice files. Okay, so you can see in the box support style system, it has taken the supports from the inside, okay, and on the outside also. Right, it has taken up all the holes. So if your part has a lot of holes or lot of missing gaps, not missing gaps, if the design is like this, where the model consumption material is not there, okay, where the voids are there into the design, so in those voids the support will taken up, okay, and it will provide a complete support structure on that particular voids or on those particular holes of your geometry. Okay, even now you can see that I have increased the wall thickness. Okay, so uh, at 1.8, okay, so the nozzle calculates the wall thickness, okay, and it divides up into the number of you can say the number of runs or the number of the wall thickness or the number of layers it will print for that particular wall thickness. So at 1.5 it was printing only 4 layers, and here at 1.8, if you can see on your screen, it is printing 6 layers now. 1 2 3 4 5 6 layers. Okay, so when so the nozzle do not deposit the material even if you choose 2 mm of 3 mm of the wall thickness, so it will not extrude a 2 mm of the thick material from the nozzle, because the nozzle size is fixed, nozzle orifice diameter is fixed. Okay, what it can do, what does it do, that it it divides the wall thickness that you have chosen, okay, into various sections, and it deposits a material as per the maximum thickness of the material that it can extrude. So the uh, I think the standard orifice diameter is from 0.3 mm to 0.4 mm only. So you can see that how the structure is building up, okay, at the setting of the 80% of the infill density and the box support structures. So you can choose the support structures as per the necessity of the geometry, as per the and you can choose the infill density as per the application, end use application. If you just want to see the form, if you don't want to apply any functional testing or do not want to apply any loads on the geometry, you can simply choose 20% of the infill density, and you can save up your printing time, your machine time, and your electricity cost, running cost, and the also the material cost that it will consume. So that's why these kind of the settings has been given for the user, so that you can play along with other settings and you can see in the slice review. Okay, so this is kind of the simulation that you can see before actually printing the object. So you can change the parameters, multiple parameters you can change, and you can see which settings are much more appropriate for that particular geometry. So if I want to use this part on the object, okay, on a particular product to be used as an end use part, so I will always choose a solid geometry or at least a 80% of the infill density, because I want more strength here, okay, on the part where it can take up the load, where it can bear the load as much as possible without breaking the part again. Uh, we have seen the auto orientations also. You can also scale up and scale down the model also. Okay. So this is a basic introduction of the GraphCAD print software, where you can change the units of the geometry, where you can choose the model material, the part building style. You can choose the infill density for that particular model as per according to the application you are going to use. You can change the body thickness. So even if in the CAD geometry the wall thickness is 5 mm, okay, you can still choose that how much of the body thickness, wall thickness. Okay, so its wall thickness, it's maximum at 3 mm, 3.2 mm, right? But you can only choose to infill the material maximum at 2.99 mm, okay, with the infill density of 29%. So that depends upon what geometry you are printing. So the maximum thickness and the minimum thickness which you can choose, it can show here that how much of the maximum and minimum wall thickness you can choose as per the geometry, and what infill style you want to print in to maintain the internal strength and also the weight of the part. Then the auto orientation helps you to calculate the best orientation possible so that it will take less amount of time to complete the object, and uh, and also to make the less support structure possible for that particular object. So I think we are done today with the basic introduction of the GraphQuad print and what are the file formats that you can load up for the 3D printing. Okay, for any kind of the technology that you can use for the Stratasys 3D printer, whether you are going to use a FDM or a PolyJet 3D printer, you can use a single machine over here. This is the build preparation uh, interface, and this is the job history. So in the job history it will show you that when uh, at what time you have started the print. Okay, you can monitor for each month, for each week also. And in the printer history, so if you are connected to a printer history into your system, and you can see that how much of the jobs has been printed, how much of the material has been consumed over the time, and how much of the running of the machine has been done. So all these things you can monitor with a single software here. So anybody has any questions regarding the formats or the GraphCAD print software, about the parameters like infill density, support density, orientations, you can please ask.
Hello, sir.
Yes.
Sir, infill density and infill pattern will affect the temperature in a 3D printed food.
No. So what is the variation that you are able to see is when
Yes.
you print the part with 20% or 50% or 80% or 100% of infill density. So the effect that it will do on the geometry is it will variate your internal strength. Okay. Lesser the infill
Yes.
density means lighter the part because the model consumption will be less. And
Yes.
if
Yes.
you're printing in a solid form, then it will give you a complete solid structure, and also it will consume more material. It will cost you more also because of more material consumption, but it will not change, it will not give you any difference in terms of the temperature. The temperature
Okay,
will
sir.
remain consistent here.
Okay, okay. Thank you, sir.
Sir, if you want to go for casting of any 3D printed part, so what kind of setting we should go for?
Sorry, can you please repeat?
If we want to go for casting of any 3D printed part,
Okay.
so what kind of setting we should go for? So what
Okay.
precaution we should?
For the casting application, the best material that we have is the ABS material. So with the ABS has that characteristics that it can melt down, okay, when you pour the molten material into the cast, and it can leave you a very less ash residue, okay, in the end. So there will be a very less toxicity into your final part, and also very less, mixture or the contamination of the material. Okay, so there will be a very less percentage of the contamination or the toxic gases that it will produce. So ABS is the best material, and for the settings, you can choose the less infill density. Okay, so you can print it at like 20% or 25% of infill density. If it is a bigger part or a smaller part, no matter the sizes. So you can choose the 20 to 25% of infill density, so that the making, the time and the cost of making of that part will be less. Okay, there you can save your cost of manufacturing the pattern, and also when pouring the molten material into the cast, it makes it easy to burn out, okay, because of the gaps inside the geometry.
Okay, thank you.
So we have actually many customers globally, and Indian customers also, through the automotive OEM or the aerospace aerospace suppliers, manufacturers, or from the automotive suppliers and the manufacturers, and even the farming equipment OEMs like the John Deere is there, and the Tafe VST tiller is there. So all these companies, they make the patterns now through the polymer, okay, through the FDM machine in the ABS material, and they cast those materials for the metal outputs. Anybody has any questions, or we can wind up? Okay, I have a question for the participants. Anybody of you currently working with any 3D printing technology for your research or for any other purposes?
I think, sir, none of the participant is working on this.
Okay.
They are just
I
new
think that
learning.
participant is not present today.
Enough participants are there, sir, but these are all participants writing
Okay,
for DFRD and other.
okay.
These are all the
So I think we can wind up now, sir.
today's session.
I think, yes, sir.
We
I
completed
think
with
there are no, if there are no further questions, I think we can wind up.
Sir, all they are new beginners in this sector, sir. So they will get learn from this. Many scientists also are there. If
Yes,
they
sir.
learn
Yes,
from
sir.
this, they can use the equipment, or maybe there may be possibility that they will procure 3D printer.
Right, sir.
So thank you for today's session, sir. Thank you all participants
sir.
for attending today's session. We will conclude this session. I will share the attendance sheet in your WhatsApp group for all participants and feedback form. So you just fill it. It will be just link will be closed in the half an hour. Okay. All participants. So thank you, sir. Thank you for the
Yeah,
today's
thank you, sir. Thank you all the participants for being a patient listener. Thank you.
I'll just end the meeting.